It's amazing to think about all the things AI can do these days. We see it everywhere.
Yeah.
Like, I was just reading about these self-driving cars that are navigating busy city streets.
Oh, yeah.
And then there are those AI systems that help doctors spot tiny details in medical scans.
Right.
Not to mention the almost magical way AI can enhance photos right on our phones.
Yeah.
Like it's second nature.
It's incredible how far AI has come.
It really is. But something that struck me while I was reading about all this is the sheer amount of computing power behind these AI models.
Oh, absolutely.
Like, we're talking systems that are reaching near human-level performance in tasks.
Yeah.
Like recognizing objects in an image.
Yeah.
But often what's powering that performance is this huge energy-hungry system, like a hidden giant.
Yeah, you hit the nail on the head there. It's one of the biggest challenges in the field right now, These advanced AI models, they're incredible in terms of accuracy and what they can achieve, but their size and the amount of computation they need can be a real obstacle, especially when you think about deploying them on everyday devices with limited processing power.
Right, like our phones or those tiny computers embedded in smart devices. It's like trying to fit a supercomputer into your pocket.
Exactly. You just can't cram that much processing power into such small spaces. And that's where this really interesting concept of knowledge distillation comes into play.
Knowledge distillation. It sounds almost like some kind of ancient alchemy, doesn't it? Like transforming lead into gold or something.
Well, in a way, it's not too far off. It's this fascinating idea of transferring the knowledge and expertise of a larger, more complex AI model to a smaller, more efficient one.
Okay, so kind of like a master craftsman passing on their skills and secrets to an apprentice, right?
Exactly. You have a large, sophisticated teacher model, the master craftsman in your analogy, and this teacher imparts its knowledge to a smaller, more agile student model, the apprentice. The goal is for the student to be able to perform almost as well as the teacher, but using far fewer resources.
It's pretty clever. So in this deep dive today, we're going to explore this whole idea of knowledge distillation, and we've gathered some really interesting resources to help us understand it better.
Oh, yeah, we've got some good stuff.
We have a comprehensive review from ArcFIF, which gives a broad overview of the field.
Yay.
We've also got insights from the 2025 Embedded Vision Summit, which focuses on the practical applications of this technology.
Absolutely.
Plus another super detailed survey, again from ArcFIF, that dives deep into the technical details.
And to round it all off, we've got a really insightful piece from The Sequence, which summarizes the key advantages and challenges of knowledge distillation.
It's perfect for anyone who wants to get a grasp of this whole area of AI efficiency,
Right, exactly.
So our mission today is to distill the essence of knowledge distillation.
Exactly. We want to extract the core principles, the benefits, and the real-world applications of this technology.
And we'll focus specifically on computer vision, because that's where it's having a huge impact.
Yeah, absolutely.
And we'll do all of this without getting too bogged down in the technical jargon.
Exactly. We want to make this accessible and engaging for everyone.
So let's get started. Let's break down what knowledge distillation actually is at its core. What's the fundamental idea behind it?
Well, at its heart, you're taking knowledge from a large, accurate AI model, often called the teacher model. This teacher model is really good at what it does, but it's usually computationally expensive, meaning it requires a lot of processing power.
Yeah, it's the supercomputer we talked about earlier.
Right, exactly. So you take this teacher model and you transfer its knowledge to a smaller, faster model, which we call the student model.
Ah, the apprentice.
Precisely. And the student model might not be quite as accurate as the teacher, but the goal is to get it as close as possible while making it much more efficient.
So it's about making AI more accessible.
Yes. More accessible and practical. The whole motivation behind knowledge distillation is to make AI work on devices with limited resources, in situations where you can't rely on a giant data center.
Right, like that drone navigating in a remote area with spotty internet connection.
Exactly. Or think about self-driving cars needing to make split-second decisions on the road. They need to be intelligent in their own right without constantly needing to communicate with the cloud.
And it's not just self-driving cars, right?
Oh, no, not at all. Think about portable medical devices that can provide immediate diagnostic analysis in remote locations where access to specialists is limited.
Those are all really compelling use cases. So to make this knowledge distillation work, what are the essential components involved? What are the key ingredients, so to speak?
Well, there are generally three main parts we need to consider. First, there's the knowledge itself. what specific information or insights are being transferred from the teacher to the student.
Okay, so what exactly is being taught?
Exactly. Second, we have the distillation algorithm, which is the method or technique used to facilitate this transfer of knowledge.
So it's the teaching method, the way the knowledge is conveyed.
Precisely. And lastly, we have the architecture, the structure, and relationship between the teacher and student models.
Okay, so how are these two models designed and connected to facilitate this transfer of knowledge?
Exactly. And in the knowledge distillation, a survey paper, there's a helpful diagram, figure 1, that visually represents this whole teacher-student framework.
Excellent. So let's start with the first ingredient, the knowledge. What forms can this knowledge take?
Well, typically there are 3 main types of knowledge that are transferred. We have response-based knowledge, feature-based knowledge, and relation-based knowledge.
Okay, 3 different flavors of knowledge. Let's start with response-based knowledge. What's the gist of that one?
In response-based knowledge, the student essentially tries to mimic the teacher's final outputs. It learns to predict what the teacher predicts.
Okay, so it's about matching the teacher's answers.
Yeah, but there's a little twist here. Instead of just using the hard labels, the definitive answers like, this is a dog, the teacher often provides what we call soft targets.
Soft targets, what are those?
Well, imagine the teacher is looking at an image and has to decide what it is. Instead of just giving a single answer, it gives probabilities for each possible category.
So instead of just saying dog, it might say 80% sure it's a dog, 10% sure it's a wolf, 5% sure it's a fox.
Exactly. And these probabilities, these soft targets, they contain a lot more information than just the single most likely label.
I see. So it's not just about the what, but also the how sure and the what else it could be.
Precisely. This extra information, it's often called dark knowledge. It captures the relationships between different categories that the teacher has learned.
Interesting. Dark knowledge. I like that.
And to make the students' predictions match these soft targets, we use a measure called Kullback-Leibler divergence loss.
I'm not going to pretend I understand the math behind that, but I get the general idea. It's a way to compare the students' predictions to the teacher's soft targets.
Right. And the survey paper illustrates this response-based knowledge distillation in figure 4. Now, moving on to feature-based knowledge.
Okay, what's that about?
Well, this is about going a level deeper.
Okay.
Instead of just mimicking the final outputs, the student tries to learn the internal representations that the teacher has developed.
So it's like peering into the teacher's thought process, trying to understand how it arrived at its conclusions.
Exactly. You're trying to replicate the features that the teacher has extracted from the data. The problem is, the teacher and student might have different architectures, different structures.
Yeah, the apprentice's brain might be wired a bit differently than the master craftsman's.
Precisely. So to align these internal representations, we might need to use transformation functions, additional layers that help translate between the two.
Okay, like a language translator helping them understand each other's thoughts.
Exactly. And to measure how well the student is matching the teacher's internal representations, we use various similarity functions.
Okay.
Things like L2 and L1 norms, cross-entropy loss, and a technique called maximum mean discrepancy.
Got it. So it's about making the student think like the teacher at a deeper level. And the third type of knowledge, you said it was relation-based knowledge.
Yes, that's right. And this one takes an even broader view.
Okay.
Instead of focusing on individual outputs or isolated features, it tries to capture the relationships between different data points that the teacher has learned.
Or relationships between data points. So like how different images are related to each other.
Exactly. For example, the teacher might have learned that images of different dog breeds are more similar to each other than they are to images of cars, even if the individual images look quite different.
Right. It's understanding the underlying connections, the bigger picture.
Precisely. And we can represent these relationships in different ways. We might use instance relationship graphs that explicitly connect different data points, or we might try to match the feature similarities between the teacher and student.
So the student learns to group similar things together, just like the teacher does.
Exactly. And we can also use probabilistic distributions to represent these relationships.
Got it. So in a sense, the student is learning not just from individual examples, but also from the relationships between those examples.
Right. And the survey paper provides some really good illustrations of relation-based knowledge distillation in Figure 7 and Table 2. Now, let's talk about the different ways this knowledge transfer can happen, the different distillation schemes.
Distillation schemes. Okay. What are the main types?
There are 3 primary schemes. offline distillation, online distillation, and self-distillation.
Okay, let's take them one at a time. Starting with offline distillation, which sounds like the most straightforward one.
It is, in a way. In offline distillation, you first train the teacher model on a large data set until it becomes very good at its task. Then you use this pre-trained teacher to guide the training of the student model.
So it's like the teacher prepares all the lessons in advance, and then the student comes in and learns from those prepared materials.
Precisely. And the student can learn from the teacher's final outputs, those soft targets we talked about, or it can learn from the teacher's internal representations.
Okay, a well-structured curriculum. What about online distillation?
Online distillation is more dynamic. In this scheme, the teacher and student models are trained together simultaneously. They can even learn from each other in this collaborative setting.
Oh, interesting. So they're both learning and evolving together. It's like a more interactive classroom.
Exactly. You might have multiple student models learning under the guidance of a single, more powerful teacher.
Okay.
Or you could even have multiple models with similar architectures learning from each other. This is called co-distillation.
They're all helping each other learn and improve.
Exactly. And the advantage here is that the whole learning process can be optimized in a more integrated way.
And then there's self-distillation, which sounds kind of intriguing.
It is. In self-distillation, a model essentially learns from a larger or more advanced version of itself.
So it's like learning from your own experiences and insights.
Exactly. For example, the deeper layers of a neural network might act as the teacher for the shallower layers.
Okay, so the more experienced part of the network teaches the less experienced part.
Right. Or a model that has been trained for a longer time could guide the training of an earlier version of itself.
It's almost like time travel, where the future self is teaching the past self.
That's a great analogy. And the amazing thing about self-distillation is that you don't need a separate teacher model at all.
You just leverage the different parts or stages of the same model.
Exactly. And there have been some recent advances in self-distillation, like DLB and MixSKD.
DLB, MixSKD, interesting acronyms.
Yeah, DLB stands for self-distillation from last mini batch.
Okay.
It uses the predictions from the most recent batch of training data to guide the learning process, kind of like constantly incorporating recent experiences.
Learning on the fly. And what about MixSKD?
MixSKD, which stands for self-KD from image mixtures, integrates data augmentation with self-distillation.
Data augmentation, that's where you create new training data by modifying existing data, right?
Right, like rotating images, flipping them, adjusting colors, things like that. In MixSKD, you mix different images together and have the model learn from these mixed representations.
So it's learning from its own creative combinations.
Exactly. Now, our outline also mentioned the role of the projector.
The projector, what does that refer to?
Well, sometimes in feature-based knowledge distillation, the teacher and student models might have quite different architectures.
Yeah, we talked about that.
And this can make it difficult for the student to directly mimic the teacher's internal representations.
It's like trying to fit a square peg into a round hole.
Exactly. And that's where the projector comes in. It's an additional layer or module that helps align the feature maps from the teacher and the student.
So it acts like an adapter, making sure the student can understand and learn from the teacher's representations, even if they're structured differently.
Exactly. It facilitates a more effective transfer of knowledge by bridging the gap between the two models.
Okay, so it's a crucial bridge between the teacher and the student.
Yes. But the interesting thing is, this projector layer is often discarded after the training is complete. Its purpose is solely to help the student learn.
It's like scaffolding that's removed once the building is complete.
Precisely. Now, let's move on to the practical side of things.
Yeah, let's see where knowledge distillation is actually being used in the real world.
Okay.
And we'll focus specifically on computer vision, because that's where it's making a big splash.
Absolutely. There are so many fascinating applications in this field. Let's start with image super resolution. Have you heard of that?
Yeah, it's about taking a low-resolution image and making it look sharper, higher resolution.
Right. And knowledge distillation can be really effective here. You train a teacher model on high-resolution images. Then you use this teacher to guide the training of a student model that works with low-resolution images.
So the student learns to enhance images by mimicking the teacher's understanding of high-resolution details.
Exactly. And the review mentioned something called super resolution guided knowledge distillation for low-resolution image classification.
Okay, what's that about?
Well, in this approach, you first enhance the low-resolution image using a super-resolution module.
Okay.
And this module itself is trained with guidance from a high-resolution teacher.
I see. So you're essentially pre-processing the image to make it easier for the student to classify.
Exactly. It's like giving the student a better set of glasses to see the image with. And studies have shown that this technique significantly improves classification accuracy even when the input images are really low resolution.
That's impressive. What about the application in infrared visible image fusion?
Infrared and visible light images capture different aspects of a scene.
Right, like infrared can see heat signatures that visible light can't.
Exactly. And fusing these two types of images can be really beneficial in various fields. For example, in surveillance, autonomous driving, and even medical diagnostics.
Okay.
And knowledge distillation can be used to train a student model that can effectively fuse information from both infrared and visible images.
Even if the student primarily operates on one type of image.
Exactly. It can learn from a teacher that has been trained on a different type of image, capturing the complementary information from both.
That's pretty cool. And what about weekly supervised learning? How does knowledge distillation help there?
Weekly supervised learning is when you have training data with limited or imprecise labels.
So you might know an object is present in an image, but you don't know exactly where it is or what its boundaries are.
Right. And knowledge distillation can be a lifesaver in these situations. You can use a teacher model that has been trained on fully labeled data to guide the training of a student model that's working with this weekly labeled data.
So even though the labels are noisy or incomplete, the student can still learn from the teacher's more complete understanding.
Exactly. And this can save a lot of time and effort because labeling data accurately can be really expensive and time-consuming.
Absolutely. Now, medical image classification is another area where knowledge distillation seems to be gaining traction.
Yeah, definitely. Medical image analysis often uses really complex neural networks, especially CNNs.
CNNs, convolutional neural networks.
Right, and these CNNs can be very computationally intensive. Knowledge distillation allows us to create smaller, more efficient CNNs for tasks like medical image segmentation and diagnosis.
Okay.
And these smaller models can still achieve high levels of accuracy, which is crucial in healthcare.
Absolutely.
There are even specialized techniques that use contrastive loss functions, things like Mano and Was, to preserve the relationships between different medical features during this distillation process.
And the survey paper also mentioned the mean teacher framework, which is illustrated in Figure 6.
Oh, yeah, that's a popular approach in this context. It's a way to make the knowledge transfer more robust and improve the student's ability to generalize.
So it's all about making medical AI more practical and accessible.
Exactly. And what about face recognition? How is knowledge distillation being used there?
Well, I imagine face recognition models can also be quite computationally demanding, especially if you want them to run on devices like phones or security cameras.
Oh, absolutely. And that's one of the main reasons knowledge distillation is being applied here.
To create smaller, more efficient models that can run on these devices.
Exactly. But it's not just about efficiency.
Okay.
Knowledge distillation is also used to improve the accuracy and robustness of face recognition models, especially in challenging conditions.
Like recognizing faces in low-resolution images or when the lighting is poor.
Exactly. There are techniques that focus on transferring the most discriminative features, the features that are really important for distinguishing different faces.
So the student learns to focus on the key details.
Precisely. And there are specialized methods for low-resolution face recognition that selectively transfer the most relevant information from a high-resolution teacher model.
It's like teaching the student to see the essential details even when the image is blurry.
Exactly. And Figure 7 in one of the papers illustrates this process.
Fascinating. Now, object detection is another core area of computer vision. How is knowledge distillation contributing there?
Well, object detection models, the ones that identify and locate objects in an image,
Right.
they can be quite large and complex. Knowledge distillation helps us create smaller, more efficient object detection models that can be deployed on edge devices.
Okay.
And there are different ways to do this. We can use the teacher's soft labels, not just for the object categories, but also for the bounding boxes that locate the objects.
So the student learns not just what the objects are, but also where they are in the image.
Exactly. We can also use anchor points, which are these predefined boxes that help guide the object detection process.
Okay.
And there's a technique called feature-based distillation, where we match the feature maps from different layers of the teacher and student models.
Matching the internal representations again.
Exactly. And there are even methods that help us choose the most informative layers for this feature transfer.
Like focusing on the most important parts of the teacher's thought process.
Precisely. And there's an interesting application called class incremental object detection.
What's that?
Well, imagine you have an object detection model that can recognize a certain set of objects.
Okay.
Now, you want to teach it to recognize new objects without forgetting what it already knows.
Ah, I see.
Knowledge distillation can help with this. You can use a teacher model that has been trained on the old and new objects to guide the learning of the student model, which has only been trained on the old objects.
So the student learns to expand its knowledge without losing its existing expertise.
Exactly. Now, the outline also mentioned tracking multiple objects and person search, which seem like very challenging tasks. They are. These are real-time tasks, so they need to be very efficient.
You can't afford to have any delays in those applications.
Right. Knowledge distillation helps make these systems faster and more efficient while maintaining accuracy. There are specialized loss functions that take into account not just the differences in predictions, but also things like classification and regression losses.
Okay.
And for person re-identification, where you need to track specific individuals within a crowd, there are techniques that use soft triplet loss.
Soft triplet loss. What's that?
Well, it's a way for the student to learn from the teacher's understanding of similarities between different people.
So the student learns to recognize and distinguish individuals based on the teacher's expertise.
Exactly. And there's a really cool technique called expert-guided knowledge distillation, or EGAL.
EGAL, okay.
It uses attention maps from a more expert teacher model to guide the student's focus.
So it's like the teacher is pointing out the most important areas of the image for the student to pay attention to.
Exactly. And this has been shown to significantly speed up person search in real-world scenarios.
Very impressive. Now, video captioning, that's another complex task.
It is. It involves understanding both the visual content and the temporal dynamics of a video, how things change over time.
Right, it's like describing what's happening in a movie.
Exactly. Knowledge distillation is being used with sophisticated architectures like spatial temporal graph convolutional networks, or STGCNs, to improve both the efficiency and the temporal consistency of video captions.
So it's about making the captions more accurate and coherent.
Precisely. Now let's talk about label smoothing.
Label smoothing, I've heard of that. It's a technique used to make models more robust, right?
Yeah, it helps prevent overfitting. When a model learns the training data too well and doesn't generalize well to new data.
Right, it's like memorizing the answers instead of understanding the concept.
Exactly. And combining label smoothing with knowledge distillation can lead to even better performance.
Okay.
But there are some nuances to consider, about how these two techniques interact.
Right.
There's an interesting approach called teacher-free knowledge distillation, or TFKD, where you have an ensemble of student networks that learn from each other.
So they're all teachers and students at the same time.
Exactly. It's a way to leverage the collective knowledge of multiple models. And researchers have also developed techniques like SKDLS, which stands for Softened Knowledge Distillation with Label Smoothing.
SKDLS.
Okay. It's a way to combine label smoothing and knowledge distillation in a more harmonious way.
So you get the benefits of both.
Exactly. And one of the papers, Figure 4A, nicely illustrates the advantages of these techniques compared to just using hard labels.
Excellent. Now, what about semantic segmentation? How does knowledge distillation help with that?
Semantic segmentation is about classifying every single pixel in an image.
Wow, that's a lot of pixels.
It is. It's a very computationally intensive task. Knowledge distillation helps by transferring knowledge from larger, more complex models to smaller ones.
Okay.
Techniques like cross-image relational knowledge distillation and structured knowledge distillation, or SKD, are used here.
SKD, okay.
These techniques go beyond just pixel-level predictions. They leverage the relationships between different images and the spatial relationships between different semantic categories within an image.
So the student learns to understand the context and relationships between different objects in the image.
Exactly. There are even specialized loss functions like structured cross-entropy loss and graph-based loss functions that are used to encourage this type of learning.
Got it. And finally, there's cross-modal distillation, which seems to expand the scope beyond just images and videos.
Yes, it involves transferring knowledge between different types of data like vision and language.
Oh, interesting. So you could have a model that understands both images and text.
Exactly. A prominent example is CLIP, Contrastive Language Image Pre-Training.
CLIP.
It learns powerful relationships between images and their corresponding text descriptions.
So it can match images to captions or generate captions for images.
Exactly. And there are more efficient versions of CLIP, like tiny CLIP, that are achieved through cross-modal distillation.
So it's about making these powerful multimodal models more practical and accessible.
Precisely. Now, the sequence article we mentioned, it talked about the advantages and challenges of knowledge distillation.
Right. What were the key advantages it highlighted?
Well, the sequence really emphasized the ability of knowledge distillation to create significantly smaller, more efficient AI models.
Okay.
And this is crucial for deploying AI on edge devices, devices with limited processing power and energy budgets.
Making AI more practical and ubiquitous.
Exactly. But it also mentioned that there are challenges involved in implementing knowledge distillation effectively.
Right, like finding the right combination of teacher-student architectures and distillation techniques.
Precisely. And navigating those challenges could be a topic for another deep dive in the future.
Absolutely. Now, let's wrap up by looking ahead. What are some of the exciting future directions for knowledge distillation in computer vision?
Well, one area that's really active is domain adaptation.
Domain adaptation, okay.
It's about transferring knowledge from a model trained on one data set to a model that needs to work on a different but related data set.
So like adapting a model trained on images from one country to work on images from a different country.
Exactly. Another important direction is improving uncertainty estimation in compressed models.
Uncertainty estimation, what's that?
It's about making the model more aware of when it's not sure about its predictions.
So it's like knowing when to say, I don't know.
Exactly. And that's really important for critical applications where you need to be aware of the model's limitations.
Absolutely.
Researchers are also investigating how to make compressed models more interpretable.
Interpretable, meaning understanding how they make their decisions.
Exactly. And there's ongoing research into the relationship between model complexity and distillation schemes.
Okay.
And of course, there's the challenge of designing better teacher-student architectures.
Tailoring the architectures to specific tasks.
Precisely.
Yeah.
And then there's the idea of combining knowledge distillation with other model compression techniques.
Like quantization and pruning.
Exactly. Those are techniques that further reduce the size and complexity of models.
Making them even more efficient.
Right. And finally, there's the broader goal of extending knowledge distillation to other AI tasks beyond computer vision.
And integrating it with other learning paradigms.
Exactly, like adversarial learning, AutoML, lifelong learning, reinforcement learning.
So many exciting possibilities.
Absolutely. It's a rapidly evolving field with a lot of potential.
So, to sum it all up, what are the key takeaways for our listeners today?
Well, the main takeaway is that knowledge distillation is a powerful and versatile technique for creating smaller, more efficient AI models, particularly in the field of computer vision.
Right.
It's about transferring knowledge from larger, more complex teacher models to smaller, more streamlined student models.
Okay.
And this knowledge transfer can happen in various ways through response-based knowledge, feature-based knowledge, or relation-based knowledge.
3 different flavors of knowledge.
Exactly. And there are different training schemes like offline, online, and self-distillation that offer flexibility in how this transfer is implemented. And as we've seen, knowledge distillation is already having a significant impact on a wide range of real-world applications, especially in situations where computational resources are limited.
Absolutely. So, by understanding these fundamental principles, our listeners now have a solid grasp of this crucial aspect of modern AI deployment.
Exactly. And that brings us to a final thought for everyone to ponder.
Okay.
Given the rapid advancements in edge computing and the increasing complexity of AI models,
Right.
how do you think knowledge distillation might evolve in the coming years?
That's a great question. How will it shape the future of AI? How will it impact our daily interactions with intelligent systems?
It's an exciting time to be following this field.
Absolutely. And if you're interested in diving deeper into this fascinating world of knowledge distillation, we encourage you to check out the research papers we've mentioned.
Yeah, definitely.
Explore the applications that have caught your attention. And imagine the possibilities of making AI more accessible, efficient, and seamlessly integrated into our lives.
That's what it's all about.
It's been a fantastic discussion.
It has, absolutely.
Thank you so much for joining us on this deep dive into knowledge distillation.
It's been my pleasure.
Until next time, stay curious and keep exploring the amazing world of AI.